Hello everyone. Is my audio working fine? We'll start in 5 minutes at 5:05. In the meantime, could you guys say something to see if the audio is working? Alright, awesome, it is working. Um, we'll, we'll start at 5:05, just to give you guys some time. In the meantime, how is everyone feeling for the exams? In my opinion, MATH2011, which is the one that I did, it seemed quite daunting at first, but when you actually do the final exam, it's not too difficult. Like most of the questions to follow the same format. Nervous? I mean, I think for most people this would be their second, the first, second level 2 maths course. So I think it is a bit of a step up from first year maths, but over time you get used to it and it becomes quite manageable. Also, while this seminar is for both the several variable calculus and the higher one, so both 2011 and 2111. We kind of structured this based on 2111, so a lot of this content is exclusive to 2111, but there are a few parts that have 2011 in them. Tons of things to remember. I mean, it's an online exam, right? So if you do forget, you can look at your notes. 94%, that's pretty good. Anyway, it is 5:05, so I'll get started. So in this seminar, I'll go over a lot of the content quickly, but I'll try to focus more on exam questions since this is what's important for your final exam. There's a lot of content, like it might seem like there's a lot of content for like in this course, but a lot of it is provided for context to help you understand the stuff that you need to know. So I'll try to skip through the content that's not as relevant for your final exam. Right. So starting off, we'll start with Fourier Series. This is exclusive to MATH2011, by the way. So we'll start with inner products. So inner products, these are things that are useful in linear algebra, but you don't really need to know them too much. They don't appear in the final exam. If there's an operation that follows these four rules, let me give it a drawing. And similarly, a norm is anything that follows these four rules. In particular, this rule is useful because this second rule. So norms have this property where if we have if the norm of a vector is 0, then that vector will be 0. So we use that often to say that two vectors are the same. So we have the norm of a minus b equals 0, then that implies a minus b is a 0 vector, and that implies a equals b. Additionally, we have, so this tells us the connection between norms and inner products. So often we can take the square root of an inner product and that will give us a norm. And the Cauchy-Schwarz inequality is something that comes up from norms and inner products. But in terms of the final exam, you don't really need to know these. So with functions, so with Fourier series, we're dealing with functions. So our inner products, we're interested in inner products with functions, and the standard inner product is just the integral from a to b of the two functions multiplied. And note that these bounds are important because if we change the bounds, then we'll get a different integral. So this inner product depends. This inner product depends on the bounds. We will have the recorded part of part 1. Sorry, they will probably be available in a few minutes once Gerald hears this, hopefully. If not, I'll tell him after the workshop and he'll make them available. So with inner products, if you remember from algebra, we have this property called orthogonality, where if we have, say, u dot v equals 0, that means u and v are orthogonal. So with functions, we kind of apply the same thing. So if the inner product of f and g is 0, then we call that orthogonal. And note that these cosines and sines, so these are the things that we use in our Fourier series. These functions are all mutually orthogonal. and this is the L squared norm. And so what we're getting to here is basically our Fourier series. So our Fourier series is a series, looks like this. I need to get better at drawing. Okay. A Fourier series is anything of this form. So we have some constant term, and then we have a series of cosines and sines. So when you introduce the Fourier series, they're compared to Taylor series because, like Taylor series, they're things that we use to approximate or to replicate functions. And the difference between Fourier series and Taylor series is that Fourier series, instead of using polynomials, we're using trig, so we're using cosines and sines. Two things that one, they're periodic, which means they can replicate waves, and secondly, they stay between a certain range, so usually -1 and 1, unlike Taylor series, which explode to infinity. And another thing is that with Taylor series, we need to find the terms, we need to differentiate. But with Fourier series, we just integrate. So actually, with Fourier series, we don't even need our function to be continuous. That's one nice thing about Fourier series. So with this Fourier series, what we need to do is we need to find these coefficients, right? Everything else is known. This L is just a period. So a lot of the times, if the period is, actually the L is half the period. So if our period is 2 pi, then L is pi. And if L equals pi, then probably shouldn't have written it. Okay, if L is pi, then the pi's cancel out. So yeah, Fourier series can replicate functions that are continuous. Also, this formula that I've scribbled all over, I believe it is it's provided at the front of your final exam. So if you forget it, then it's right there. And actually, the formula for these coefficients is also there, I think. So why did we go through all those inner products and norms? Well, if you remember from algebra, what we can do is we can use, if we have an orthogonal set of vectors, then we can project any vector within that vector space onto these set of vectors using these projections. And so with Fourier series, we kind of use the same idea. Instead, we're not using the dot product and the Euclidean norm. Instead, we're using the inner product with functions, which is the integral of fx times cosine x, and we use the L squared norm as the norm. And notice with so when we use this formula, we don't actually have to do this bottom part, this norm, because actually the norm for all these functions is all equal to L, where L is the period. So, sorry, where 2L is the period. So if our period is 2 pi, then we just get this 1 over pi over here. So these are how we get our Fourier coefficients. We just take the integral of fx multiplied by cosine with the n going up, and our bounds are just the bounds of the period. And notice how I said n starts from 0. So going back, so here this first term, we can just write it as a0 because a0 or a02, they're both constants and a0 can be anything. In this course, we use a0 over 2, and the reason for that is it's just nicer so that when we apply this formula, we can use the same formula for a0, so we don't need to adjust a0. Like we just find a0 and then for a0 over 2, and that's our first term. With odd and even functions, so this is something that you should note. It's something that you can recognize. It helps with finding your Fourier coefficients. So if a function is odd, that just means it's symmetric about the origin. So let's say it looks like that over here, then it looks like that over here. That might not be exactly symmetric. And if it's even, then it should be the same. So it's symmetric over the y-axis. So this is even, and odd would look something like that. Now, they don't have to look like that. I'm just saying these are examples of what odd functions and even functions would look like with their symmetry. And so with our Fourier series, we're replicating these functions using cosines and sines. And hopefully you know that cosine is I keep scribbling everywhere. Cosine is even and sine is odd. So if we want to replicate an odd function, it would make sense that we replicate it with odd functions. So if we have an odd function, then generally we just use our Fourier series just becomes a sum of sines. And we can ignore all the cosines. So basically what happens is all the ak becomes 0. Okay. And when we have an even function, then all the bn's, so all the coefficients for sine become 0. Yeah, I noticed we had a 2018 workshop just then that I was watching, and I noticed that with their first term they just use A0 instead of A02. So I think you just have to be careful with that. Although I think if you do make that mistake, hopefully lecturer will be lenient because it is like a reasonable mistake, and it's, I don't know. Okay, so when we have once we've calculated our Fourier series, we have to check if they actually converge to a function, because otherwise maybe we just came up with some series for no reason and it doesn't actually help us do anything. So we explore 3 different types of convergences. They all have their respective epsilon definitions, but I didn't really go through them. Intuitively, pointwise just means the function converges at every point. So basically, for every point, we can apply the epsilon definition, and it converges. Uniform convergence, that just means it converges everywhere. So when we apply the epsilon definition, we have to apply it for all x within this boundary. So we can't just do it for each x. We have to do it for any x. And the mean squared sense convergence it just converges in this using this mean squared norm. Piecewise continuity, again, it's another definition. For the exam, you don't really need to know these too well, but these definitions they get used in other things, which is why they're taught. So intuitively, piecewise continuity, it's in the name. So if you could break a function into, let's say, you can break a function into continuous pieces, so that's why it's piecewise continuous, and that means, if you can break a function into continuous pieces where we have a finite set, so a finite number of, wait, no, that wasn't the right one. Actually, it was. If we can break a function into a set of finite set of continuous pieces, then it's piecewise continuous. The nice thing about piecewise continuous functions is that it means we can integrate them. So remember, to find our Fourier coefficients, we need to find fx of cos kx, or it could be k pi x over L, and also for the sine. And so we can't actually find this if these integrals don't exist, right? So if f is piecewise continuous on this closed and bounded interval, that means we can find this fx, and usually that means we can also find this cosine x. This coefficient. However, just because we can find these Fourier coefficients, again, this doesn't mean that the series will converge. So all of this doesn't tell us much. It just means that we can find the coefficients. Similarly, piecewise differentiability, that just means it's similar to piecewise continuity. We can break it into a series of differentiable pieces. And again, if you remember the definition of differentiability, you just have to apply the limit definition. Although I think for your final exam, you won't really be asked on this. So from all of that, what we get is that when we get this result, so if we have a function that is 2L periodic, usually 2 pi periodic, so basically it just needs to be periodic. The 2L just means we know it just helps to specify that the period is 2L. It is piecewise continuous on this boundary, on this region, and if these positive and negative these positive and negative limits of the derivatives exist, then we know that at every point C, where f is continuous at C, then the Fourier series will match the function. And otherwise, where it's not continuous, so say we have a jump discontinuity, then the Fourier series will be halfway between the two sides. And this tells us what our Fourier series will look like. So if we have a function that's continuous, essentially if we have a function that's continuous and these derivatives exist, then our Fourier series will copy this function exactly. And this isn't periodic, but let's just say it's a part of the function. And if we have some interval, so we have some jump interval, then our Fourier series will just copy it, and then here we have this continuity, so it'll just jump down and then it'll follow it. This tells us how to graph what our Fourier series will look like. Also tells us a bit about the convergence, although it doesn't really specify what type of convergence. So here we have an actual test. So the Weierstrass test, so this test is used to tell if a function converges uniformly. So sometimes if a question asks to prove that the Fourier series converges uniformly, then this is the test we use. Back to purple. So it says let fk be a sequence of functions defined on this interval AB, and suppose we have another sequence that serves as an upper bound for this absolute value of this sequence. Then if this sum of ck converges, then fk will converge uniformly to a function f. Here the Fourier series aren't mentioned, but essentially this is what we use to tell our Fourier series converge uniformly. So here we have a past question. Also notice, so for my slides, all of my examples are from MATH2011 because I didn't have access to any MATH2011 papers. But the questions I don't think they're too difficult. They're too difficult, so I think some of them can be assessed in MATH2011 if you're doing that. Although Fourier series is not part of that course. So we have a function that's defined as minus x plus pi for x between 0 and pi, and x plus pi between minus pi and 0. And here this tells us that it's 2 pi periodic, so the period is 2 pi. Pi was to sketch the function. I removed that, but I'll also do that. So what does it look like? So let's look at the first piece. So when x is between 0 and pi, so let's say pi is here, then f of x is minus x plus pi. So at 0, that would be pi, and then just be a straight line down. And on the left side, between minus pi and 0, it's like the negative of that. So instead of minus x, we have x. So at 0, it would still be at pi, and then here at minus pi, it goes down. And here, this tells us it's 2 pi periodic, so we can keep going and it'll look the same. And it'll look like that. So for part B, find the Fourier coefficients for this Fourier series. So this is usually the standard question they start with because in order to work with our Fourier series, we need to know what the Fourier series actually is. So we just plug in the formulas. So actually, I think I'll remember it. Hopefully you guys remember it as well. So AK is just integral from minus pi to pi of f of x times cosine of, we'll just write kx because period is pi, so in the formula it's k pi x over L, and L is pi, so the pi's cancel out. So we just have this. Little trick here, this function is even. You can see in the graph, and actually you can mostly just see in the graph. So what you can do is, since f is even and cosine is even, then f times cosine, even function times an even function is even. You should be careful with doing that though, because it's not the same as with numbers. So with numbers, an even number times an odd number would be odd. So it would be even, but with functions, an even function times an odd function is actually, wait a second. Wait, no, it's still odd. Okay, I think I confused myself. Anyway, this function is even though, because wait, why is that? Alright, so this function is even. If this function was odd, well then our integral from minus pi to pi would be 0, right? Because we're integrating from minus pi to pi, and you remember integral is just the area under the curve with the signs taken into account. So if our function is odd, well then this area would cancel out this area and the integral would be 0. However, our function is an even function, so we should have, so our A coefficients should not be 0, otherwise our Fourier series will be 0, because we know bk is 0. I kind of went on a tangent here. But anyway, bk is 0 for all k because our function is even, so we don't need the sign coefficients. So going back to ak, this is even, because an even function times even is even. So what we can do is we can split it, we can change the bounds 0 to pi, since both sides of the both areas, like the areas on either side will be the same. So fx times cosine. And the reason why we did that is because here our f is piecewise, so in order to evaluate this integral of fx, we need to break it up anyway. But this way we don't have to break it up because we recognize that it's the same on both sides. So not the same, but if we calculate the integral on either side, it will be the same. So now, since our bounds are between 0 to pi, that's just this first one. So that's 2, 0, pi, minus x plus pi, cosine k of x dx. So when you're doing this, yep, odd times odd is even, that's what I meant, even though I didn't say that. So with these, often you often get some function and then some cosine, and the way to do this is typically using integration by parts. So if you've done a lot of these, hopefully you should be able to do it without thinking too much. So we'll split it up into 2, 0 pi, actually, let's do that, x cosine kx dx plus pi, 0 pi, kx, don't have enough space, but okay, so applying integration by parts, so we differentiate x, that becomes 1. Actually, no, we don't do that yet. We get x, we integrate cosine, so that's sine kx over k, 0 pi, and then minus, minus, differentiate that, so 0 pi sine kx over k dx, and then plus this part, that is pi over k, so the k comes out, sine kx. I think I'm out of space. But anyway, if we plug this in, this will all become 0 because sine of pi times anything was 0, and 0 times 0 into the x is 0. Probably faster set u equals minus x plus pi. Yeah, honestly, I was a bit lazy with this when I was writing the slides, so actually I didn't actually do this, but I believe this also cancels out, and you just get this second term, and that becomes I think you get 1 over k squared. You get a double negative, so it's like cosine kx 0 pi, and so here we get and this is a bit tricky, so when you sub in pi, what is cosine of k times pi? And that depends on k, right? So essentially it becomes minus 1 to the k, because so say we have 1, so k is 1, and cosine of pi is just minus 1, so that'll be negative. And if we have 2 pi, then cosine of 2 pi, that would be 1. So basically it just switches between minus 1 and 1, so minus 1 to the k, that works fine. And when you plug in 0, that's just 1, so looks like that. And I've cleaned it up on the next slide, thankfully. So, yep, so it becomes this. 1 is on the other side. But anyway, after some integration by parts, we get this. And then you have to check which values yep, so check which values work. So when k is even, then this becomes 1, and these two cancel out, and it all becomes 0. So when k is even is 0, and when k is odd, we get 1 minus minus 1, which is 2, and multiplied by 2, we get 4 over pi k squared. And bk is 0 because once again the function is even, so we don't need the odd terms. Sorry. Oh, actually, one thing to note is that this we can't do this if k equals 0 because we can't divide by k. However, I think if you plug k equals 0 into here, you get, so a of 0 just becomes 0 pi. Cosine of 0 is 1, so you get minus x plus pi dx, which is sorry. I think it all cancels out. So yep, so here, which equals to 2 over pi, so we get minus pi squared over 2 plus pi squared, and then the zeros are all 0. So I think I might have okay, I think I'm making mistakes somewhere. Pi. But anyway, ignoring that, we get probably a bad example, setting a bad example. But after doing that, you get the Fourier coefficients, which is what we needed. So moving on, part D that asks, does our Fourier series converge uniformly to F? So this is asking whether it does or not. So it doesn't actually tell us whether it does. We don't really have an explicit way of showing it doesn't, because it's like with convergence, you can't just come up with a counterexample. However, with uniform convergence, that's like a relatively strong form of convergence. So if you show that it doesn't converge at all, then that would mean it doesn't converge. So one way a Fourier series wouldn't converge is if the F isn't continuous, because that means like if we have Fourier series, because our Fourier series is continuous, and if the function that we're replicating isn't continuous, then we can't replicate it at every point. However, this function is continuous, as you can see by this graph. So let's say it does converge uniformly. In that case, we just apply the Weierstrass test. So remember, our Weierstrass test was that, if we can find a sequence Ck that serves as an upper bound to the absolute value of our functions. So we know that Fk, after we put the coefficient and the cosine together, then Fk is equal to whatever A0 was, plus integral of, it's like 4 over pi cosine x plus, and it's only for the odd case, so it's like 4 over pi times 9 times cosine 3x, and so on. So we need to find an upper bound for this. And actually, note that if we take the absolute value of this will always be greater than 0. So actually, even though Fk, our Fourier series is, our sequence is only this for our odd case, we can actually say it's less than or equal to 4 over pi squared cosine k pi. Well, I was meant to fix this. This is an x. Why is it? Why am I getting so confused? Yeah, I think this should be an x. Sorry. So this sequence, which is equal to this for our odd k, will be less than or equal to this for all k, right? Because this is always greater, because our Fk is equal to 0 otherwise, and 0 is less than or equal to this. And then now we have this function, and we know cosine is always between -1 and 1. So if we take the absolute value, that's always less than or equal to 1. Oh, and also took out the pi here because the pi also the pi also decreases the value. So 4 over k squared, we can use that as the upper bound. And if you remember from first year, using the P series test, this sum 4 over k squared, since our p value is 2, which is greater than 1, this sum will converge. And so by the Weierstrass test, because we have a ck, which is just 4 over k squared, which is an upper bound for our fk's, then our Fourier series will converge uniformly to f. Moving on, we have Piecewise theorem. So Piecewise theorem is another way we can show that a Fourier series converges. Although looking at the exams, I haven't seen it too much. But essentially, if we have a function that is periodic and bounded, and this is square integrable, basically if you integrate the square from the bounds, you'll get a finite value, then the Fourier series will converge in the mean squared sense. And if this theorem holds, then we can apply Piecewise identity which is just this. So here we have another question. So again, we need to determine the Fourier series. I think it's always good to start with graphs, with a sketch. So see what it looks like. And again, this is 2 pi periodic. So when x is, the absolute value of x is less than or equal to d and greater than or equal to 0, although it should always be greater than or equal to 0, then the function is 1. So that means from minus d to d, this function is 1. And then from between d and pi, it is 0. And same on this side. So again, here you can see that this is an even function. Also, to maintain, well, it continues since it's periodic. So to determine the Fourier series f for the function of f. So once again, we just use the formula. So our L is pi since the period is 2 pi, so 1 over pi. The integral fx times cosine x. Again, we can apply this trick because this is even, so we can change it from 0 to pi. I think, although this isn't always necessary, earlier I did it because we had a piecewise function which had 2 separate functions for x less than 0 and x greater than 0. Here it's probably not necessary, but I did it anyway. And again, once again we have a piecewise function, and the way to do that is to split it up. So with any integral, you can always split up the bounds. So integrating between 0 to d and integrating from d to pi, this is the same as that. And then we know that when x is between d and pi, then f is 0. So this whole thing becomes 0 because we're integrating with 0 times cosine x dx will just be 0. And fx is 1, so we're just left with integral of cosine. And I added these dots there, but it's not really that many steps. You just get 2 over pi times 1 over cosine sine kx from 0 to d. Sine of 0 is 0, so we just get sine of kd, and with 2 over pi k. However, you should be careful of k equals 0. So we can do this for k greater than 0, but if k equals 0, we can't just take out the k because we can't have 1 over 0. But here is fine. What you do is you go back to this step, and because all the above is still true regardless of what the k is. So you go back to this step, and when k is 0, that's just 0. So cosine of 0, which is just 1. So 1 dx, which is just 2 over pi x from 0 to d, which is 2d over pi. So that's our a0. This is our ak. And our bk, well, what would our bk be? So as I said earlier, our function is even, so bk is just 0 for k. Yep, I've done that here. Also, in this case, the question asks to actually write that Fourier series, so you should write it out. And remember, with our formula, the first term is a2 over 0, so a0 is this, and we divide by 2 to get d over pi with our first term. Also, don't forget your cosine. It's not just the sum of the coefficients, we also need the cosine and a sine, but we don't have a sine here. So part C asks to use Piecewise identity to find this. It's quite messy actually. It's done a lot of real messy working, but essentially you just take Piecewise identity, so this is essentially it. But I've just plugged in all the values, so instead of L it's pi. This is a0, which is 2d over pi, and then this is just, ak, which is just this. So after a bit of work, bit of manipulation, it's a bit of steps which might be a bit messy, and you just do a bit of manipulation, move things around, calculate this integral, which isn't hard because f is just 1, and we end up with what we want on one side, and we can find out what it is equal to. I kind of rushed through that because I think I took too long on Fourier series. So our next topic is vector fields. Actually, I kind of made up these. I kind of chose how to break up these sections myself. So I believe in the course you were given 6 sets of lecture notes, 6 sets of notes. I just combine them into 4 topics. So vector fields, this is really more of a precursor to line integrals. On its own, it's not. I guess there are a few questions, but they're generally not too difficult. So what is a vector field? A vector field is just a map of every point to a vector. So really, a vector field is, you can also call it a vector function because it's really the same thing. It's a vector function because it's a vector of functions. So in 3D, you have 3 components, and we can break it up into 3 functions. So essentially, it's just a function from some m-dimensional domain. So it doesn't have to be not from the reals anymore. Not just from the scalar, and to some other domain. And to sketch them, well, we can only sketch them in 2D, but to sketch them in 2D, we just draw a bunch of arrows. And the arrows, if you remember, with vectors, the direction represents, the direction, and the length represents the magnitude. So here, I've taken this directly from the lecture, from your notes. You can see the arrows, and this represents a vector field. So realistically, a vector field would be continuous, but we can't draw infinite arrows, so we try to draw them spaced out to kind of show what's happening at every point. So here, I think these were winds. So here the arrows are very short, so there's not a lot of wind here, and then here the arrows are long. You can see that the wind is mostly traveling that way. It gives an idea of what's happening at every point, basically. I'm actually not sure why they introduced a flow line. I've never seen that anywhere. But a flow line is just anything that satisfies this definition. So with vector fields, we have 3 operations. Or the first one's the gradient. So let's assume you already know that. I think it's taught early in the course anyway. And all 3 of these, they use this symbol. The operator is called del, although the symbol is called nabla. So if you want to type that in LaTeX, that's \nabla. But handwriting LaTeX class anyway. Essentially, this actually I shouldn't have this F here. This nabla basically represents this operator, which is like a vector of these partial derivatives. The operator, so del is an operator, it's not a vector, but in many ways it's kind of like a vector, as you see in the following. So for gradient, we kind of apply this del to a scalar function. We essentially, you remember when we have a vector times a scalar, then we just multiply them out individually, and that's like what we do here. That's really so that's kind of how the notation works with the delta F. Divergence is like the dot product of del with F, or this time F is a scalar field, and we just add them together. So it's called a divergence, and the reason for that is that it represents the divergence of the flux, so how the flux is traveling outwards. So if we have a positive divergence, that means that the total flux is moving outwards at some point P. And when we have a negative divergence, then it's the opposite. The flux is generally coming in. So basically, if you draw the vector field, then at some point all the arrows are pointing in, then that would mean that the divergence here would be negative. And when we have zero divergence, then that we call that incompressible. Yeah, essentially, so del is the name of the operator, and del is the name of the operator. When we apply del to a function, then that becomes that becomes a gradient. Just a bit of naming. If you convert it into symbols, then it's all the same. So here we have a question. With these questions, they're pretty easy. You just do it, right? So divergence of F, that's just the dot product. So we just take the derivative of the first one. Well, actually, it produces a scalar, so it's not a vector, so we don't need this, actually. So just take the derivative of the first one with respect to x. Well, that's just 1, because it's a partial derivative, and there's no x here, so that becomes 0. And plus, because it's a dot product. So the derivative of the second component with respect to y, again, it's a partial derivative, so we don't care about the x and the z. So we get 2y divided by x squared plus y squared plus z squared. And there's also a minus from this minus up front, which I probably should have done first, but I didn't forget it. And then we take the derivative of the third component with respect to z, but there's no z here, so that's just 0. And so the divergence is just this. You can really do this without thinking too much, as long as you remember the definition. It might help to remember that divergence is like the dot product, because that's how it's written, right? And lastly, we have the co. And the co here is like the cross product, because, well, you can see. So essentially, we just take it's like taking the determinant of this, where we have the three partial derivatives and then the three components of the vector field F. Again, with cross products, like with vectors, we can only take cross products with three-dimensional vectors. It's not really defined otherwise. And here again, when you ask for the co, we just assume that F is three-dimensional. Although we can also do it with a two-dimensional vector field, because in that case, what we do is we let this one be 0. And the interpretation, it's in the name, so it's like how the vector fields swirl around. So a positive co would mean that the vector field is swirling in the anti-clockwise direction, or counterclockwise, as it's sometimes called. If co is 0, that means it's rotational, so essentially the overall... actually, sorry, this only applies to two-dimensional cases. It's a bit hard to picture how a vector field can co in 3 dimensions. So in 2 dimensions, essentially that's the intuition or the interpretation. Yep. So here we have another question. Although this one is it's a bit of work, but I think you can do this by definition. So this is kind of doing by brute force. Like there might be a nicer way, but just doing it directly by definition, you can do without thinking. So, and that's often the best way to. Well, that's always something you can do during exam. So we want the co of the gradient of some function, of some scalar function phi. So it's called scalar field, and that just means it's a scalar function. So apply the definition. So what's the again, since we're using the co, we assume that this this function phi has 3 components. So then so we start with the gradient, and that's just partial x. Wait a second, sorry, I meant it's a scalar field. Sorry, it doesn't have 3 components. It's a function of 3 variables. 6. Okay. So our gradient is just derivative with respect to the 3 components. And actually it's taking too long to write out. So I've done it here. So start with the gradient, it's just this. And because phi is C2, we know that this exists. And then we find the curl, so plug that into here. And we just find the determinant of this. And when we find the determinant, remember, so how we do it, we start with one component, and then we find the determinant of this submatrix. And if you notice, because phi is C2, the partial derivatives mix, so that mixed partial derivatives commute. So this minus this will be 0 because they cancel out. Well, we have yz and yz. And here we have xz, xz, and xy, xy. So essentially, this is all equal 0 because they all cancel out. So that's the end of vector fields, and we'll move on to line integrals, which is where vector fields are kind of used. So we start with path integral actually, and a path integral is just a line integral where where our function is a scalar rather than a vector field. And we compute it using this formula, although I don't think I saw any path integral questions in your final exams. But essentially, the path integral serves as a nice introduction because it's easy to understand. It's like instead of integrating a function along the x-axis or along the y-axis, you can integrate along some path, which can be anywhere in between. So it's a bit like a directional derivative, but like for integrals. With path integrals, when you let the function f equal 1, then you can find the length of some path or some curve C. And like regular integrals, they have the same properties, so they're linear, so we can split them up. So we can take the lambda out and get lambda f of 1 and separate it and get plus the integral of f2. So integrals preserve, line integrals preserve linearity. So I meant path integrals, but line integrals also do. And you can also split the bounds, like with a regular integral. Should I just notice it's not quite 6 o'clock. I think I can slow down. If anyone has any questions at any point, just ask them in the chat. So from path integrals, we get line integrals. And the difference between them is that with a line integral, we're integrating a vector field instead of a scalar. Although actually the names are used interchangeably because path integrals are also line integrals. They're called, we also call them scalar line integrals. And in old past papers, they're called line integrals, path integrals. So it is very confusing. But the way to tell is just look at the integral itself. If we have a vector field or if we have a scalar function. So here with a line integral where we have a vector field, then it starts with this form, and the way you compute it is that you find some path C, which parameterizes this curve. Just draw a curly. Okay, that is not the way. So you find some path that parameterizes this curve where t between a and b, and then you compute this integral. And this second line is just shows the relationship between this line integral and the scalar path integral. So remember, a path integral is just the function of ct times the norm of of C dash. Or also, and this norm refers to the Euclidean norm, which hopefully you remember from algebra in first year. This norm is just to show the relationship between the path integral. If you want to find the line integral, you just use this one. And essentially the line integral is the integral of the tangential component of f, if that explains anything. I think they're mostly used in like physics because when these are introduced, they mostly talk about flux, which is like something to do with force fields, I think. I don't do physics, I don't know. Anyway, so the work done by a force field F acting on an object can be calculated using this line integral. So that's essentially the purpose. That's usually how we interpret line integrals. It's just calculating the work by a force field. So the reason why we have these line integrals is that with force fields, right, they're applied everywhere, and they're essentially just a bunch of like at any point there's a force, and it can be in any direction, so we represent it by a vector. So that's why we have to integrate a force field. A vector field. So sometimes line integrals are written in this way. Essentially, what they mean is that it can be written like this, and the way to interpret it is that if you chuck in a dt, and then you throw in a dt at the front, that's essentially like dt it's not a number, so you can't just. But in some ways you can just play around with them. And so this dx dt becomes x dash. So this dx dt, well, these x, y, and z come from this path. So from this formula, we can write it like this. So we plug in the CTs into the m, n, and p, and we replace the dx by x dash, dy with y dash, and dz with z dash. Now this just becomes the integral on t. So this just becomes a regular integral, and we can compute this. So here we have a question. Compute the line integral. So you can use the formula from the previous slide. Right, so here we have our path is 1t et, so plug it in, so comes integral. So the bounds are from 0 to 1, so 0 to 1, 2 cosine. So z is et, so we have et, and dx, so x is 1, so x dash is 0, because that's just a constant, plus x, that's 1, and dy becomes y dash, so y is t, so derivative of t is 1, and then 3e to the y is t, and then z is et, so z dash is also et, and then with respect to t. So we can compute this. So this is 0, so that's just 0. That's 1 plus 3e to the 2t dt. And hopefully you know your integrals. That's 3 over 2 e to the 2t 0, 1. So you plug in 1, you get 1 plus 3 over 2 e squared, and then plug in 0, that's 0, so minus 3 over 2, e to the 2 times 0, that's just 1, so minus. And so that's just what you do. I think that's relatively straightforward. So if you get a question like this, then it's very nice because it's just 3 marks, as long as you don't make any mistakes, but hopefully you shouldn't. So yep. And 1 minus 3 over 2 is minus half. Here with another question, although this is really just an inspection question. It's just testing your understanding. So we have a vector field G, which is illustrated. We don't have a formula. It's just that. And we have a curve C, which illustrates our path. So is this path integral? So notice here, with the question they said path integral, even though this is a vector field. So does this path integral, is this path integral positive, negative, or 0? And C is oriented clockwise, in case you can't see this arrow here. So really you can just, I think with this question you can just look at it and answer it. So you can see here we're traveling, all the arrows are pointing that way. Keep traveling, the arrows are still pointing out that way, so they're pointing against us. And you keep going along, you notice that the whole way through, the arrows are always going against, so always going against the flux. If you're going against the flux, essentially if the flux represents, so if the flux applies a force, then that will slow you down. So the work done on you will be negative, so this path integral should be negative, because we're going against the flux. Some properties of line integrals. So again, like regular integrals, they're linear. So we have some linear combination of vector fields. In this case, we can break it up. We can break up the integral. If you change direction, if you reverse the orientation, that's like swapping the bounds around. So you get the negative of whatever you had in the first place. And if C is a union of smooth curves, I think I might have skipped that earlier, but no, I didn't. But essentially, actually, I haven't really defined what smooth is. But essentially, you can break it up into the bounds. So that's like with our so with our regular integrals, we can break it up, right? Where C, in fact, C doesn't actually have to be between A and B; it can be anywhere. So we can break up line integral as well. So this brings us to the fundamental theorem of calculus for line integrals, which is like the fundamental theorem of calculus, but for line integrals. That's why it's called that. Anyway, so it says that if we have a function phi, where the phi is like the antiderivative of f, so if we take the gradient of phi, we get scalar function f, then we say f is conservative. You can also call it a gradient field because it's a vector field and it's a gradient, so we can call it a gradient field. And this phi is called the potential function. So if this phi exists such that the gradient of phi is f, then for every oriented curve, since we're dealing with line integrals, we can say that the line integral of this vector field f through this curve is just phi applied to the endpoints, where Q and P are the endpoints of C. So this is like the fundamental, this is pretty similar to the fundamental theorem of calculus that you're familiar with. So remember, if you have an antiderivative, then that's just capital F of P minus capital F of A. And here's pretty much the same thing. It's just that with these vectors and stuff. And also these phi's don't always exist. So that's the key part. We're not sure if phi exists, but if it does, then we can use it, essentially. And some nice properties that if f is conservative, so if this phi exists, then if C is closed, then our integral becomes 0. So basically, if C is closed, so the path we're integrating is some path that ends up where it started. Then basically P will equal Q, right? Because they're both the same point. And so phi of q, so phi of p minus phi of p, or whatever, this will be 0, and so that's why the line is equals 0. And also with this, so this doesn't take into account which path we've taken, it just takes account the endpoint. So if we have a conservative f, then the choice of path is irrelevant. Now I notice I haven't really taken a break, but I think I've gone quickly enough that I'm not too far from finishing. But my voice is dying. Anyway, we have another example here. So we have a vector field that's defined as 2xy in the first component minus z in the second component and x squared in the third component. And we need to evaluate this line integral from this point A to B through the straight line segment. So here they haven't told us, they haven't given us the parameterization, although in this case it's not too hard to come up with ourselves. So this is a straight line, so the easiest way, especially since these three components act the same way, we can just say our path. So you can say CT will just be T, and T, or T from 0 to 1, right? So if we plug in 0, we get 0, 0, 0. If we plug in 1, we get 1, 1, 1, which is just A and B. And this will be a straight line. So this works. So we want to find the line integral. So we apply it. So we have so remember what you do is you essentially take the dot product of f with c dash, apply that f. So I have 2xy, so actually I can scroll. Okay, can I write small? So basically x, x, y, z come from here. So x is t and y is also t. In fact, all of them are t. So I'll just write. I'll write using transpose. So actually, that doesn't work. Okay, so we have 2xy, and all the x, y, and z are t, so that's just 2t squared. Wait, so let me do this. Minus z is minus t, and x squared, that's just t squared, because all of them are t. And we take the dot product of with c dash, so c is t, so see that c dash is just 1, 1, 1. Since we're differentiating in all respect to t, so just 1, 1, 1. dt, and bounds go from 0 to 1 because that's where our path goes. So this is just essentially you just add them up, so 0 to 1, 2t squared minus t plus t squared dt. So we move the t's together, 3t squared minus t, and that's just t cubed minus t squared over 2, 0, 1. If you plug in the zeros, there was 0, so just 1 cubed is 1, 1 is a half, and that's just half. Yep. Now for part B, a question asks, would the integral be the same regardless of the path taken between A and B? Explain why or why not. So this might sound familiar. We had something that sounded similar in the fundamental theorem of calculus. So if f is conservative in this point, if f is conservative, then the choice of path is irrelevant. So essentially, if f is conservative, that means we can find some phi such that there exists a phi such that phi, I'm just going to use all the shorthand notation. is equal to f. So if this is true, then we know f is conservative, and this would be the same. If it's not the same, then it's a bit tricky actually. We'll need to find. I think we need to find a counterexample. So let's hope it's the same and see if it works. So we need to find to show that the same. We need f to be conservative. So we need to find some scalar function. We need to find some scalar function nabla such that the gradient is f. I need more space. Let's just clear all this. Okay. Okay, I can't be bothered. Let's just use a different color. Just ignore the marks. Okay. So we need to find a nabla such that the gradient of nabla is equal to f, which is 2xy minus z and x squared, I think. Yep. So how do we do this? So we compare. In order for two vectors to be the same, each element must be the same. So we start with the first component. And actually, so before we do this, if you're, you can try just doing trial and error because it's not too difficult. I think you can get there with a few tries. Show that the curve of f is 0. Wait, what is the curve of f equals 0? Show that. Can you explain why curve f equals 0 shows that they're the same? In the solution they used they just used this they just found the potential function, so I think this is a surefire way that'll work. So we want the first one to equal 2xy. Okay, so we want the partial of the respect to the first component to equal to 2xy. So we integrate. So these are partial derivatives, so we can ignore the y. That becomes x squared y plus some constant c. However, this is not. However, this is not a constant. This is just a constant with respect to x. So it can still be a function of y and z. Because remember, if we take the partial derivative of this, if there's no x in here, then it's the constant with respect to x, but it can still be a function of y and z. So now let's differentiate with respect to the second component. dy goes to 2xy. Wait, no, sorry. And this becomes x squared plus, I'm going to use this notation here. So this just means partial derivative with respect to y. Actually, I probably shouldn't use that. Okay. You might notice this doesn't, the second component of f is z. There's no x squared, there's no x here, but here we have an x, and this partial derivative of c, y, and z won't cancel out the x because it's not a function of x. So you might think that it's not, it doesn't work, but So you might see that these two might not be the same, but you can actually find that this is equal to this this third component. And basically what we can do is these y and z's, they don't have to be necessarily in order. So when we take the gradient, we take the derivative with respect to the first component and then the second component and then the third component. But like whatever is the second component, whatever is the third component, doesn't have to be fixed, right? So we can swap them around. So let's say y is the third component, then the derivative of this, then this should be equal to x squared, which means the derivative with respect to y of c of yz will be 0. So that means we have phi is x squared y plus some function of z, because we still need to check for z. And so we check, so we take the derivative with respect to z, that's equal to, well, this is not a function of z, so we get c dash of z, and that's equal to minus z. So we have c of z is equal to it's minus z, so minus z squared over 2. So we can get our potential function after swapping z and y around will equal it's a scalar function. X squared y minus z squared over 2. And we can add a constant here, but it really doesn't matter because we're only interested in the gradient. So essentially we found a potential function, which means f is conservative, since if we take the gradient of this, that will equal f. So f is conservative, and that means that yes, this integral would be the same regardless of the path taken. And notice we can use this to check part A. So we have this, and remember A is 0, 0, 0, and B is 1, 1, 1. So we plug this into phi. So we plug this into phi. So we plug 1, 1, 1, that will equal 1 minus half, which equals to half. When we plug in 0, 0, 0, that would be equal 0. So phi of B minus phi of A equals half. And that's another way to do part A. So actually, if you like taking a bit of a gamble, you could try to do part B first. Find this potential function and use that to answer part A. However, if it doesn't work, then that means you've wasted a bit of time. So it's up to you if you want to do that. But I think if you do the usual way, using the path C, and do part B afterwards, then you can use that to check the answer for part A. And I think that's probably better. And lastly, for line integrals, we have Green's theorem. So Green's theorem says that we'll have some conditions. So let's say we have some region D, which is bounded and simple. If you remember the definition for simple, that just means it doesn't just cross itself. Wait, I think. I should stop saying that. Anyway, we have some conditions. So if D is bounded and simple, and this boundary C is oriented in the anti-clockwise direction, and if M and N are both continuously differentiable, then we have this identity essentially. So with the questions, do we need to identify the constant? No. So what we were doing is that we just need to find a function phi. We just need to find a function phi such that the gradient of phi equals f. So the phi can be anything. So if we add a c, then that would give the general form of phi. But we don't really need that. We just need to show that a phi exists. So Green's theorem is just this identity. Essentially, it's a bit of a formula. it just converts a contour integral. I didn't really explain, but a contour integral is just the integral where you go back to where you started. So it's just it connects a contour integral with a double integral. That might not seem that great because now you have to do an extra integral, but often it makes problems more simpler. And I noticed in the lecture notes they give you two forms of Green's theorem, which I found a little confusing. But if you look at them closely, the formula is actually the same. They just swap the m and n around, so it's a bit confusing. But this formula is consistent, so it's the same for both. And in past with exams, often they'll just ask you to use Green's theorem, or they have a contour integral, and they'll give you hints that you'll need to change it into a double integral. And so you just plug it into this formula. So here I have an example of that. So here we have a circle, x squared plus y squared equals 4. So that's the circle with radius 2, centered around the origin. Origin in the counterclockwise, that's in the positive direction, which is what we needed, right? No. So use Green's theorem to evaluate this integral. Right, so it says in order to evaluate, we just need to differentiate. So we swap these around, take the derivative of n with respect to x minus m with respect to y. So here you can see that this is m, and this is n. So this would be equal to double integral of d, where d is this region inside this circle. And we differentiate n with respect to x, so that's just 7. This is a partial derivative, there's no x here, so it's just 7. And then minus the derivative of m with respect to y, and that's just 2, because e to the x squared is not it's not a function of y. So then we just get that dx dy. And this might be a lot to integrate. So here we have a double integral, but actually, if you remember what a double integral is, a double integral is just you're integrating a function, so a surface. So you're integrating a function over an area, and what it calculates is the volume under that surface. Since this is constant, so this is just 5 dx dy. Essentially, we have, actually I can't really draw, it's in 3D. But basically, we have some region, when it's basically, we just get a cylinder of height 5. So we just need to find the area, so that's just, so the integral, so the area of the circle, since the radius is 2, remember r is 2, not 4, then the radius of the circle is just r of 2 squared, and then we multiply by 5. And so our integral becomes 2 squared is 4, so that's 20 pi. Another way you can think of it is you can move the 5 outside because it's not a function of x or y, it just becomes that. So essentially Green's theorem is just taking a line integral and just plugging into this theorem and getting a double integral, and then you find the double integral. And moving on to the final topic, which is surface integrals. So a surface integral is just a line integral, but with an extra dimension, essentially. So instead of going over some line, some path, you're integrating over some surface. It's quite similar. So again, we have some parameterization, which maps out the surface, and we use that to evaluate our surface integral. So instead of taking the norm of C dash, we take the norm of the cross product of these two, and this is actually the normal. It's like the normal vector. So essentially, so t is the partial derivative of phi with respect to the first component of u. Tv is partial derivative with respect to the second component v. And when you take the cross product of two vectors, remember that's just you get the normal, like it's like when you have to can't really draw it. But essentially you have the normal. And so the way you compute a surface integral when it's given like this is you find this, you take this phi, plug it in, and you find the normal, find out what your domain D is, and then you just get a regular double integral. And I say regular, probably haven't done that many double integrals, but double integrals, you turn them into iterated integrals and they become just two regular integrals. So we can find the surface area this way. If we define our function f to just be 1, then we get the surface area. So as I said earlier, this norm t, cross product of tu with tv is the norm. So sometimes they just write n instead of this, and they mean the same thing. Here we also have a definition of smooth. I think I'll just skip that actually. A lot of times you just assume that functions are smooth, like the questions will just tell you, or like they're made of elementary. Actually, yeah, so most of the time you just assume they're smooth, I think. Well, also note, so like with line integrals, surface integrals, they can be applied to both scalar functions and vector fields. So here we started with is here. I just drew all of it. Here we start with a scalar function, but we can also do vector fields, as I'll show later. Although I think they don't usually ask too many questions because it's a lot of work and it's really all the same. So we're asked to find the area of this surface, which is defined by this for this boundary. So you might notice that, so you might see that it's in this form, which you might not like, because you might be used to seeing it in terms of some f, x, y, z. And that's fine, we can always just translate it pretty easily. So we can say f of x, y, z is just move the z over, and then when we get f of x, y, z is equal to 0, then that gives us our surface. So we have this f somewhere here, and then we need to find this norm. So we need to find some phi, some parameterization in terms of two variables, and that's quite easy. It's really just given to us. We just use x and y. Since we have z in terms of x and y, then we can just say that's x is x, y is y, and z is xy. Then we can find our two gradients. So differentiate with respect to x, that's 1, 0, y. Ty is 0, 1, and x. And then we need to take the norm of the cross product. So you have I, j, k, 1, 0, y, 0, 1, x. I think I did that later. Yep, so we have this, and then compute that, so that's just n, what's the notation? N of xy, and then we take the Euclidean norm, so that's the square root of the sum of all the components squared. So this is our this is our norm, and so to compute the surface area, we just need to take the double integral of this area. So to compute this, well, it's not that nice because Also, we have to remember the boundary D. So you remember D is just the area inside the surface, so it's just the area within this circle of radius 2. And essentially what we do is with circles, easier way is just to convert to polar coordinates. So we let x equal r cosine theta, y equals r sine theta. And then our bounds become r goes from 0 to 2 because our circle is of radius 2 and we want the area inside that. And our phi goes from, our theta goes from minus pi to pi because we want the full circle. So we change this double integral into this repeated integral where we have in respect to r and theta, we sub in this r cos theta and r sin theta into x and y. And remember, when we change variables, we also have to multiply by the determinant of the Jacobian. Hopefully you remember, when you're converting to polar coordinates, it's just r, because we have so Jacobian, I forget which one goes where. Essentially, we just have the derivative of r cos theta with respect to theta, that's minus r sin theta. And then you differentiate r sin theta with respect to theta, that's r cos theta. And then we have differentiate with respect to r, so cos theta, sin theta. So you take the determinant, that's minus r sin squared theta, minus r cos squared theta, that's minus r, and take the absolute value, so you get r. So you get this iterated integral, and the cosine and sines cancel out, and you can do all this integration, and you get the answer. So moving on, so that was surface integrals on scalar functions. Again, we can also have surface integrals on vector fields, and it just becomes this formula. So pretty similar to line integrals, and we can also compare them to surface integrals on scalar functions like this, although you don't really need to. Then lastly, we have two theorems. So we have Stoke's theorem and the Divergence theorem. So Stoke's theorem says that we have some conditions, and essentially we can go from this curl of f to this line integral. So I have a question here from 2016. So I have this surface defined by x squared plus y squared plus z squared, where z is restricted to this bound. And we want to use, we have a vector field which is y, z, x, like here. And we want to use Stoke's theorem to determine the path integral. So again, it says path integral, but this is a vector field. So we just apply the formula. So this constant integral just becomes this double integral of the curl. So I think this is like the theme for Math2011, especially for the second half. A lot of time there's a lot of content, but really it just boils down to a bunch of formulas. So here we're just using this formula or this theorem. So we just take so now we just have to find this integral instead of what we had before. So we take the cross product of f. So f is we take the curl. So y, z, x, and that's with respect to x, respect to y, with respect to z, and that gives us, so first component is d of dx with x, 1 minus y with respect to z, that's 0. Second component, should be First component is y with x, which is 0, and z with minus z, so that's minus 1. And with second component, x with x, that's 1, y with z is 0, so we get 1 minus 0. And because of the second component, we switch the sign. And with the third component, we have x and z, that's 0, and y with respect to 1, y, so that's minus 1. So this is just minus 1, minus 1, minus 1. Now we just need to integrate that across this surface S, where S is this surface. Oh, okay. Also, so once we do this, we need to find some parameterization phi, so we can evaluate this integral. And I kind of jumped ahead. So instead of using xy and x squared plus y squared like I did earlier, I just jumped into polar coordinates, so r theta. So x just becomes r cos theta, y is r sine theta, and z squared equals x squared plus y squared. So and x squared plus y squared will just be r, right? So r cos squared plus r squared cos squared plus r squared sine squared is r squared, and so z will just be r. Oh, in that case, I think I made a mistake here. In that case, when you differentiate with respect to r, that would be 1. And so it becomes, so first see r, we differentiate with respect to r. So that's cosine theta, sine theta, and 1. And secondly, we differentiate with respect to theta. So that's minus r sine theta, r cos theta, and 0 since there's no thetas there. Take the cross product. So the first one would be should be minus okay, so we have cos theta, sine theta, and 1 minus r sine theta, r cos theta, and 0. So first component is minus r cos theta. The sign doesn't matter because we take the norm of it. At least way in the second component is r sine theta, and third component is r cos squared theta minus r sine squared theta, so it's just r, I think. Yep. So we end up with this. So our double integral. So so evaluating the integral of the divergence of f due to Stoke's theorem, right? So we take so if we go back, but not that far back, it's just to evaluate this, you just take the dot product with this norm. So take the dot product of this with what we found, r sine theta and r. If you remember, the cross product was just minus 1, minus 1, minus 1. So this becomes r cos theta minus r sine theta minus r. And now we just need to write the double integral with respect to r, with respect to theta. R goes from 0 to 0 to 1, and theta goes from minus pi to pi. And you can just evaluate that. Oh, here's my backup paper. Okay, so we have integral from, which I think I'll do theta first. So from minus pi to pi. So remember, you can always switch the order of the integrals. So r cos theta. R sine theta minus r d theta dr. So if I evaluate them one at a time, so there's a minus r sine theta plus r cos theta minus r theta minus pi to pi dr. So if you sub in pi or minus pi into sine, that becomes 0. So you're left with cos of theta, cos of pi, and cos of minus pi is also the same. So you just get 2 pi r. I think there's a minus. Respect to r, so pi r squared, 0, 1, and that just becomes pi. Let me check the negative sign. I think the negative, might have made a mistake with the negative sign. I think I made a mistake with the negative sign somewhere. Anyway, then finally, our last theorem for today is the divergence theorem. The z value is 1, not r. I think I fixed that right. Yep, I think I fixed that. Okay. So with divergence theorem, this is our last theorem, and in a way it's just a step up from Stoke's theorem. Now we're taking a double integral and turning it into a triple integral. And that might sound crazy, like why are we always doing more integrals? But usually it helps to simplify things. There's not really too many questions on divergence theorem, because I feel like they just chucked it onto the end of the course. But if they do ask it, they often just tell you to use it. So here, sorry. So here we have a question, and it tells us just to apply the divergence theorem. So it just tells us explicitly. So so we don't have to worry about the conditions, because we assume that we can use the divergence theorem. So we have a vector field F, which is defined like this, and we need to find this double integral. Okay. So we apply the divergence theorem. That is, we just convert this into triple integral, where V is the volume contained inside the surface S. And we just do that. So del dot product of del of F, if you remember, that's the divergence. So you take the sum of the derivatives essentially. Wait, I should stop switching too quickly. So differentiate the first component with respect to x, that's 2xy, plus differentiate this with respect to y, 3y squared, and differentiate that with respect to z, 1, and that's what we get when we apply our divergence, like so. And now we need to integrate it, and well, v So V is just this cube, which is very nice because it means our integral just becomes very easy, right? We just integrate from -1 to -1 for all x, y, z. Doesn't matter which order. So we just essentially just do this 3 times. So let's start with x. Doesn't matter which one, what the order is. So start with x. So -1 minus. That's just the 1. So integrate with respect to x. So that's x squared y plus 3xy squared plus x from -1 to 1 dy dz. That scared me. Equals oh wait, my power's turning off. My room went dark. God damn it. Anyway, let's just quickly finish this. So sub in 1 minus 1 into x. So this is x squared. So if sub in 1 and minus 1 into x squared, that gives you y minus y, which is 0. So we have -1, 1, -1, 1, and we have plug in y into this. We just get 6y squared plus 2 dy dz, and can do it again. So we have -1, 1. So it was y squared. I think there's a square there. Y plus 2 y dz. Do it again. 3y squared 2y. Sub in 1 and -1. That goes. You get 3 minus 3 because -1 squared is also 1. So essentially you get 4 from -1 to 1. dz. Did I miss one? I did, didn't I? Damn it. Okay. All right. 3xy squared. Wait, what happened? Still streaming. All right, the power went out. Okay. But essentially, if you evaluate this triple integral without making any mistakes, unlike me, you should get your answer. And that concludes this. Workshop. Sorry for the mistakes. I'll fix them up before we upload them, hopefully by tonight. Well, thank you for coming, and also that concludes our workshops for this term. These recordings will be available on this same channel that you're watching them now. So if you want to watch them, then they're available there. Otherwise, thank you all.